Hi, my name's Tom. I'm a PhD student at the University of Sydney under Scott Kroom and Jesse Vandersand. I'm going to talk to you today about some of the work I've done on Mach correlation functions applied to SAMI galaxies. So the kind of question that we're trying to get at with this work is to look at the kinematic morphology density relation. This is a relationship between lambda Re and environmental density in galaxies, where lambda Re is the spin parameter for galaxies, which can be thought of as kind of a measure of how much of the motion of stars within galaxies is ordered compared to how much is random. So it's known that galaxy stellar mass correlates both with environment and the intrinsic properties of galaxies, such as spin. So the question starts to become whether or not the relationship between spin and environmental density is a real relationship on its own, or if it's driven purely by this stellar mass relationship we know about. So some recent results suggest that maybe, yes, it is driven purely by stellar mass, although some others show that while mass may be a primary driver of this effect, environmental dependence may still exist as a weak secondary effect. So this is kind of what we're trying to look at with this work. Okay, so for our first set of observations for use for this work, we have the SAMI Galaxy Survey. So the SAMI survey contained 1,832 galaxies with lambda Re measurements. And for our work, we took a volume limited sample in redshift and stellar mass. So we took galaxies with a redshift of less than 0.06 and a mass of greater than 10 to the 10 solar masses. So that's contained within this black box here. The reason we did this was because in each of these redshift samples, we actually have significantly different distributions of stellar mass. We ended up, if we use the whole sample, introducing quite a large bias in the mass marked correlation functions. And in taking this volume limited sample, we avoid this issue. So we ended up with an overall final sample of 710 SAMI galaxies. The next set of observations we took were the gamma galaxies. So gamma served as a background galaxy distribution for this work in order to trace the large scale structure we see. So we again took a volume limited sample, but this time in redshift and R band apparent magnitude. We did this in order to, again, avoid a bias introduced by a higher density of fainter galaxies at lower redshifts. So our volume limited sample was for a redshift less than 0.06 and an apparent magnitude of less than negative 17.29, which was just an approximation of the maximum apparent magnitude at a redshift of 0.06. So this resulted in a final number of 5,576 gamma galaxies. And finally, we looked at some mock observations of galaxies in the Eagle simulation. So these galaxies were subject to a mass cut of greater than 5 times 10 to the 9 solar masses. This gave us 5,587 galaxies with lambda Re values, and then a further 29,737 galaxies which were not subject to this mass cut served as the background, again, to trace a large scale structure. So that's kind of doing the role of what the gamma is for the SAMI galaxies. And what we did was, finally, we resampled the Eagle galaxies to match SAMI's mass distribution. So I'll just quickly show here the SAMI and Eagle galaxies in a mass lambda Re space. And you can see in the top panel that the mass distributions for SAMI and Eagle are quite different. So we simply sampled Eagle galaxies to match SAMI so we could more easily compare our results at the end between them. So correlation functions, what are they? So you can see in our first equation, the probability of finding two galaxies separated by a distance s is equal to the average density of galaxies squared multiplied by 1 plus the correlation function multiplied by the volume elements those galaxies are found in. So the correlation function can be thought of as kind of the overdensity of galaxies at a specific separation. In practice, we use an estimator to calculate this. So we have 1 plus our correlation function is equal to SAMI gamma pairs divided by SAMI random gamma count pairs. So in order to calculate our SAMI gamma pairs, we simply take a SAMI galaxy and then define it at R equals 0, and then define radial bins around it and count how many gamma galaxies are in each of those radial bins and add a count for each one. And then for the denominator, the SAMI random gamma pairs, we do the same thing, except instead of our gamma sample, we introduce a pseudo-random gamma sample by simply randomizing the redshifts of our gamma galaxies, which in effect washes out the large-scale structure we see. The correlation function is often modeled as a power law, you see here with these specific parameters. This is just a graphical representation of what I was talking about in the previous slide. So we take a SAMI galaxy at the center, define our radial bins. You can see in the first bin, we have 1 gamma galaxy, so that bin gets a count of 1. And in the second bin, we have 2 gamma galaxies, that gets a count of 2, and then we repeat out until maximum radius, and then repeat for all SAMI galaxies. So now mark correlation functions. So what we do first of all is we have to assign each galaxy a mark corresponding to some physical parameter. In our case, we use stellar mass and lambda RE. And instead of using the actual values for these parameters, what we did was we used a ranking system where simply the galaxy with the lowest stellar mass gets a ranking of 1, and then so on, and a galaxy with the lowest lambda RE gets a ranking of 1, and so on. And we did this again so we could more easily compare our results in the end, because of course stellar mass ranges from 10 to the 7.5 to 10 to the 12, and lambda RE ranges as a ratio from 0 to 1. So giving them the same dynamical range by ranking them makes it easier to compare. So the mark correlation function can be thought of as a ratio of galaxy marks to the mean galaxy mark as a function of galaxy separation, and it can be shown to be equal to 1 plus a weighted correlation function over 1 plus our regular correlation function. So the weighted correlation function is calculated much the same as the regular, as we already showed, except instead of adding 1 for each gamma galaxy we find in a bin, we add the mark of the central SAMI galaxy divided by the average mark. So we have 1 plus a weighted correlation function over 1 plus the regular correlation function. We're going to attempt to model that as a power law. So we have 1 plus a power law over 1 plus a power law. Maybe it's 1 plus a power law again. So 1 plus a times s minus m. So these are our first results. So we have ranked lambda RE marks on the left and ranked stellar mass marks on the right. The blue dots are our real results, whereas the orange dots are the results we get when we randomize the marks for all our SAMI galaxies as kind of a test of our method. This should be consistent with 1, which they are. And then the red line is a fit to the power law using an MCMC algorithm with 100 fits in the chain from the algorithm plotted in the lighter red to kind of show the spread of the fits. And then in the inset, we have the distribution of the A and M parameters in our power law fit plotted there. So you can see on the left side, we have a anti-correlation of spin with environment for the SAMI galaxies. And on the right-hand side, we have a positive correlation of mass with environment for SAMI galaxies, which is consistent with previous work. For our next set of results, what we wanted to do was test the idea that, first of all, the spin anti-correlation with environment could be explained purely through the mass relation. So if that was possible, it should be further possible to, given a galaxy and its stellar mass, assign it a spin based on that and then reproduce the spin environment anti-correlation. So in order to kind of test that, we sorted our SAMI galaxies into mass spins, and then for each galaxy assigned it a spin from another galaxy at random in its own mass spin, and then tried to reproduce the ranked lambda RE plot. And you can see that we don't recover the anti-correlation of spin with environment on our left-hand side. And on the right-hand side, what we did was we simply removed all the slow rotators from the SAMI data set and reproduced the ranked lambda RE result, and found that we do still get an anti-correlation of spin with environment. So the result is not driven purely by stellar mass or by slow rotators. And then finally, we have our results for the Eagle galaxies. And we see on the left that we have an anti-correlation of spin with environment, and on the right that we have a positive correlation of mass with environment. So we get the same qualitative results with SAMI and Eagle.
You have 1 minute? Oh, perfect.
Okay, so our overall results, stellar mass is positively correlated with environment, which is consistent with previous work. Galaxy spin is negatively correlated with environment. This negative correlation of spin with environment is not driven purely by stellar mass or purely by slow rotators. And mock observations from the Eagle simulations give consistent results as compared to observed data. Thank you.
All right, thank you so much. It was very theory or very formula heavy, so I'm pretty sure people might need a bit more time to wrap their heads around the formulas. In the meantime, can I ask a very low level question? Can you explain again what the galaxy spin refers to for somebody who is not really working in the field?
Okay, so So the spin parameter is a ratio basically of ordered motion to total motion within a galaxy. So the ordered motion is basically galaxies, orbiting around the galaxy plane, for example, whereas random motion, which is given by the velocity dispersion, is kind of just like random motions within the galaxy. So a galaxy with a high lambda RE, most of its motion, is supported by rotational motion, and a galaxy with a low lambda RE is mostly supported by just random motions.
Awesome, thank you so much. All right, it looks like we still don't have, oh wait, Matthew has it. Since spin is induced over time by torques, don't you expect that spin should decrease with density for low enough densities?
I'm not entirely sure on that. That's an interesting point. I'm not entirely sure, sorry.
No worries, no worries. Yeah, that's a good thing with Slack. Don't worry, you don't have to answer now. Luca has another question. He's suspecting that the agreement with Eagle is only qualitative, not quantitative. But still, can we learn anything from the quantitative mismatch?
Yeah, that's a good point. So obviously we see the qualitative results are the same in the sense that we have, the negative correlation and positive correlation, but it's difficult to compare the A and M parameters exactly because they are a bit different between them. I know that we haven't looked too deeply into what we can actually tell exactly from the quantitative values of A and M, for example. It's more been a study of the qualitative results at this point. So it would be interesting to see what we can find from, comparing how A varies between the two data sets, but we haven't done that at this point.
All right. Sounds like a cool idea for follow-up.